Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. I'm actually sneaking in this video. I really was not intending to do another one, but in this series for the fundamental identities and the basics for trig functions, it's always nice to have a single video that's about how to prove trigonometric identities. And so this is that video. This does not assume any knowledge of the double angle, half angle identities, the sum and difference identities, and the sum to product and product to sum identities. This only assumes that you know the cofunction identities, the odd and even identities, the Pythagorean identities, the reciprocal identities, and the ratio identities. Those are the ones that you would have seen up to this point in my video series already. But you could still cover quite a bit of ground in this video as far as showcasing how you would prove trigonometric identities. So let's talk about that. As I mentioned in the previous video, when you're faced with a proof, you need to prove a trig identity, start with the most complicated side. Now, it is often going to be the case that you start with the complicated side and you get stuck. Well, if that's the case, you can always go to step 5 there and try the other side. So these are just pieces of advice, rules of thumb, but they're not actually hard and fast rules. So you do not have to follow these in the order given. You don't have to follow these at all. It's just that these are suggestions. So start with the most complicated side is what I would suggest. Use known trig identities if you can, if there's any there. Use algebraic manipulations. These are things like if there's a difference of squares, a sum of difference of cubes, if you can multiply by the conjugate, that type of thing. These are algebraic manipulations you know all the way up to this point in mathematics. If all of that fails, write everything in terms of sine and cosine. That is often for me an early tactic, but for many other people, they don't do that tactic until way later on. And then finally, like I said, if you get stuck, try the other side. So let's try these tactics on like 4 more problems. And the problems that I've chosen to try these on are problems that I think are good, decent level problems that would cause most beginning trig students a little bit of trouble. So let's go ahead and take a look at this guy. Obviously, between the two sides, the more complicated side is going to be the left-hand side. So I'm going to go ahead and focus on working on the left-hand side there. And what I'll do is maybe say left-hand side here is equal to, and I'll just rewrite it. It's not that big of a deal to take a few moments to rewrite it. Pay close attention to the variables that they give you, also to the signs, because obviously I just miswrote that. So in this case, they're giving me the variable x as my argument. That's perfectly fine. And this is just an algebra problem, honestly. Multiply things out. So it's a binomial distribution. So 1 times 1, 1 times cotangent squared. So that's a plus cotangent squared of x. A negative cosine squared times 1. So negative cosine squared of x. And finally, a negative cosine squared times a cotangent squared. Negative cosine squared times a cotangent squared. Now, obviously, that does not look like the number 1, and they tell us that should be the number 1. But the good news is I have a number 1 right there. So the rest of this must cancel somehow. So let's see how the rest of this will cancel. Let's see manipulations here. That cosine squared times a cotangent squared is often a big sign that things will start to cancel, but it's not a guarantee. In fact, as I'm looking at this, I can see 3 different identities I could take advantage of. So let me showcase what I mean by 3 different identities I could take advantage of. I could do my algebra first and factor by grouping. That is, I could factor cosine squared out of this group. If I do that, I will end up, specifically if I factor out a negative cosine squared, I'll end up with a 1 plus cotangent squared. And that is a cosecant squared. So that's an identity I could totally take advantage of. Or if I take the very first of these trig functions, the cotangent squared, and group it with this negative cosine times cotangent squared, I can factor out a cotangent squared from those two. And I'll be left with a 1 minus cosine squared, which is a sine squared. So that's another way to tackle this. So let me just showcase all, well, not all, but some of the different ways you can do this. So one way, I'll write it in green here, is I'll group together the cotangent squared. So I have a cotangent squared minus a cosine squared times a cotangent squared. And then I still have this minus cosine squared hanging out, just waiting for something magical to happen. But what I'm going to do is, now that I've rearranged that, I'm going to factor a cotangent squared from those 2 terms. When I do that, I get 1 plus a cotangent squared, and I'm left with a 1 minus cosine squared. Now, like I said, there are a lot of ways to do this, so this is not the only way. But now that I've gotten there, I know that 1 minus cosine squared is another way of writing sine squared. That's from the Pythagorean identity, which I'll just go ahead and write up here. Cosine squared of an angle plus sine squared of an angle, the same angle, is equal to 1. And so if I subtract cosine squared from both sides, I would get that sine squared is 1 minus cosine squared. That happens so often in trigonometry that you really want to just be able to see that and move on it very quickly. So I happen to know that 1 minus cosine squared is going to turn into a sine squared. So I'll trade it out right now. That's a cotangent squared. And then we have a beautiful sine squared of x. And then we still have off back there a minus cosine squared. And if you're stuck at this point, then change the cotangent to be written in terms of sines and cosines. The cotangent, as we know, is the cosine of x over the sine of x. But it's not the cotangent, it's a cotangent squared. So it's going to be cosine squared over sine squared. And we still have the sine squared here, minus cosine squared. You see the sine squareds cancel beautifully. And you have cosine squared minus cosine squared. I'll actually write that extra step in just so you can see it. Plus cosine squared of x minus cosine squared of x. And now you can see this does compress all the way down to the number 1, which is what we wanted to show. That's the right-hand side of our equation. That's one way you could have done this. Yet another way, the very first step, by the way, everybody's going to do that. Everybody's going to multiply that stuff out. Another way you could do this, and I'll do this in blue. So let me put a little dividing line here so you can see that I'm trying something else. I'll take that black ink there. I'll keep the number 1, like I said, like I did before. And this time, I'll write everything in terms of sines and cosines. A lot of people will do this. It's not necessarily the fastest way to do it, but it gets the job done. So we get a cosine squared over a sine squared. Let's see, minus cosine squared. And then finally, minus cosine squared times a cosine squared over a sine squared. And that looks like it's not very attractive, but notice you can get them all in the same denominator. So the common denominator here is sine squared. So I'll just write cosine squared. I'm going to have to zoom in a little bit. Cosine squared of x. That is over a sine squared. And then the next term, this guy right here, I'll multiply top and bottom by sine squared. So I get a sine squared of x cosine squared of x. And then the last one is a minus cosine to the fourth of x. And these are all over sine squared. Now you can see it's not really a super attractive way of doing this problem, but notice that in the numerator, every single term has a cosine squared in common. So I can go ahead and factor that out. I have a cosine squared of x over sine squared of x, and I'm left with a 1 minus sine squared minus a cosine squared. And there is a Pythagorean identity right here. 1 minus sine squared, write it up here. Cosine squared is the same thing as 1 minus sine squared. 1 minus sine squared. So if I trade out that 1 minus sine squared right here for a cosine squared, we have what we need. This is 1 plus cosine squared of x over sine squared of x times a sine squared, cosine squared, sorry about that. Cosine squared of x minus cosine squared of x, which is 0. And so therefore, this is going to be 1. And there are several other ways you could do this problem. I just showcased a couple of them. And that's what I like about proofs, is that it requires you to be a critical thinker. There's no algorithm for doing it. There's suggestions, but there's no real true algorithm. And this is why it kind of gets frustrating for students, but some students really love this. Actually, a lot of students really like the proof parts here. They can be very, very rewarding as far as showcasing your skills. Here's another proof, or another identity they'd like us to prove, and I'm specifically handpicking problems that showcase different tactics. And so this guy right here, the previous one was kind of random. There's a lot of different tactics you could have used, but this one, there really isn't a lot of different tactics. It's pretty much one tactic. First of all, the left-hand side is the most complicated side, so the left-hand side is where I'm starting. I'll just start with that. Left-hand side is equal to, I'll zoom in. It's a 1 over secant of x plus tangent of x, and then plus a 1 over secant of x minus tangent of x. Just double check that. Yep. And we want to get to a 2 secant. That's our goal. Well, these two fractions should be added up, so we need a common denominator. Now here's where this tactic showcases, or this problem I should say, showcases a common tactic within proofs. Very, very common within a proof that if you have a fraction and let's say in the denominator you have some type of sum like that involves trig functions, you would multiply both numerator and denominator by the conjugate. So that's what I'm going to do here. You're kind of forced to do it here because that's the common denominator. But this is my advice in general, is if you have a problem that has fractions and it's a single fraction on one side, let's just say, you can try multiplying both numerator and denominator by the conjugate of that denominator. It's a really good tactic. It often works. So I'm just doing that here. And I think what I'll do is I'll pause the video while I finish handwriting this stuff out. There we go. So notice that I've used parentheses liberally here because if I don't, then I'm only multiplying that tangent by this picture. I really want to multiply that entire denominator by that expression. So now that they have common denominators, I'll go ahead and glue them together as a single fraction over that common denominator. So the common denominator is secant of x plus tangent of x times secant of x minus tangent of x, which by the way is a difference of squares formula. The numerator is going to be secant of x minus tangent of x. plus secant of x plus tangent of x. And you can see in the numerators the tangents cancel and the secants combine to become a 2 secant. And what I'm going to do in the denominators, I'm going to go ahead and distribute those binomials. And again, that's like an x plus y times an x minus y. That's a difference of squares. So it's going to be a secant squared. Notice I'm using my algebra minus tangent squared. The algebra is going to be with us for the rest of our mathematical career. So if you dislike algebra, then you're going to have problems. It's just going to be bad news. I'm going to write down off to the side here one of the Pythagorean identities. There's one that's 1 plus tangent squared of x should equal secant squared of x. And if you look at that denominator, it's secant squared minus tangent squared. So if I subtract tangent squared from both sides, you will see secant squared minus tangent squared is actually 1. So I'm going to trade that out for the number 1. 2 secant of x over 1, and that's just going to be 2 secant of x, which is exactly what we wanted to get. Again, the tactic here was multiplying numerator and denominator by a conjugate. That was one of the reasons why I wanted to make this video, because that's such a common tactic that I just wanted to make sure you had seen an example using it. As I was building an assignment for my students, I realized, whoa, I should have talked about that in that video that I previously did. And I created this problem, and I love this problem, not just because I created it, but because it involves a lot of tactics. So if you look between the two sides, they're both actually complicated. This is a great example of a proof where you have to work on both sides, not simultaneously, but where you start on a side, you get to a point, and then you go to the other side and kind of clean that side up as well. You can see they're both kind of a little bit ugly. So I'm going to go ahead and still start on this left-hand side because it technically is the uglier of the two sides. And here's what I imagine most students would probably do. They'd look at that left-hand side, they'd write, okay, I have a cosine cubed of x minus a sine cubed of x. Right then and there, they might be able to recognize that's a difference of cubes. And so that would be awesome if they did. If you recognize that was a difference of cubes, then good for you. That is exactly what it is. So I'm going to go ahead and take advantage of algebra here, and I'm going to factor that difference of cubes. And it's just a prerequisite for trigonometry, so we're just going to quickly do this with very little explanation. So it's cosine squared of x plus cosine of x times sine of x, and then finally plus sine squared of x. And this is all over that denominator, which I believe that a lot of people will look at and not know what to do with, but we'll discuss that in a moment. All right, a couple things I want you to really pay attention to. Always look for identities, things that we have proven so far in this course. And I see one, so I'm just going to mention it over here. Sine squared plus cosine squared of the same angle is 1. And if you didn't notice it, I'll highlight it. We have a cosine squared plus sine squared right there. So those two will combine up to become the number 1. But not only that, we also have from an earlier video that the sine is an odd function. So sine of negative x is actually negative sine of x. So that's this picture right here, sine of negative x. We're going to trade that out for a negative sine of x. And finally, this guy right here, that when you see a trig function of pi over 2 minus something, that's a cofunction identity. We know from the cofunction identities, sine of pi over 2 minus x, that is the same thing as the cosine of the x. In other words, cosine of an angle is sine of its complement. So I'm going to do those trades now. So again, in the numerator, I'm just going to rewrite that cosine minus sine. So cosine of x minus sine, again, of x. Don't forget to write those of x's. Times cosine squared plus sine squared is 1, plus cosine of x sine of x. And like we said, in the denominator, the sine of pi over 2 minus x is a cofunction identity for the cosine of x. And sine is odd, so sine of negative x is minus sine of x. And if you note here, the numerator has a picture identical to the denominator, and those factors will cancel beautifully. And this ends up becoming a beautiful 1 plus the cosine of x times the sine of x. Now, is that the right-hand side? And the answer is no, it's not the right-hand side. The right-hand side is 1 plus the cosine of negative x times the cosine of pi over 2 minus x. So we're going to look at the right-hand side now, and we're going to clean that up just a little bit. So I'm just going to write this in here. This is such a common tactic to partway through just jump over to the other side. It's not that you're adding or subtracting, multiplying or dividing between the sides. It's that you're focusing on one side until you get to a point, a stopping point basically, and then you hop to the other side and see if you can wiggle that other side to be the same. Well, cosine is even. So cosine of negative x is cosine of x. So I'm just going to go ahead and rewrite that. That's 1 plus cosine of x. And that is a cofunction identity. The cosine of pi over 2 minus x. It's the same thing as the sine of x. Oops. Again, the sine of an angle is the cosine of its complement. And so I will trade that out for the sine of x. And now you should notice the right-hand side and the left-hand side are equivalent. I have wiggled the right-hand side down to an expression that is the same as what I wiggled the left-hand side down to. And so our proof is done. We've proven it to where the sides meet. And that is the end of the proof. Really nice way to tackle a trigonometric identity or a proof for a trig identity. The final example I have in this video, I had in a different video. And I forgot to actually, in this case, I forgot to write the expression. So anyway, I had something like this in a different video. The only thing I didn't have was this last piece. Assume that your angle is between 0 and pi over 2 radians. In other words, assume that theta is in quadrant 1. And that becomes important if you're given that. We can take advantage of it. So let's see what happens when we take advantage of that. Well, I'm going to let x equal 5 secant of theta. Let's go ahead and do that here. This would therefore be the square root of something squared minus 25. That's something being 5 secant of theta. And the denominator would be 5 secant of theta. When you clean up the radicand, you get 25 secant squared of theta minus 25, all over, again, 5 secant of theta. Notice both terms in the radicand can be factored or have a 25 in common, so that can be factored out. And the square root of 25 is 5. So this is 5 square root of, and then secant squared of theta minus 1. And this is all over 5 secant of theta. The 5's obviously cancel. But I want to draw your attention to something else. There's a trig identity involving secant squared. It's 1 plus tangent squared of theta is equal to secant squared of theta. This is a Pythagorean identity that has to be memorized. You subtract 1 from both sides, and you get that tangent squared of theta is equal to secant squared of theta minus 1. That is, this secant squared minus 1, I can trade out for a tangent squared. So that's what I'm going to do here. Remember, the 5's will cancel, and I get the square root of tangent squared of theta, and this is all over secant of theta. Now, in the previous lecture video, I mentioned the square root of x squared is the absolute value of x, and that is totally true. However, I'm going to write it here. It's the absolute value of tangent of theta, and then I'm going to say the if part, or secant of theta. If that picture within the absolute value is positive, there's no need to have the absolute value. And because we're in quadrant 1, our angle was told to us to be in quadrant 1, all of our trig functions are positive in quadrant 1. So that tangent of theta, it's positive. Therefore, we can remove the absolute values. So we have a tangent theta over a secant of theta. And then at this point, I would just rewrite everything in terms of sines and cosines, because it's actually a little bit cleaner. So we'd have a sine of theta over cosine of theta. That's the tangent. And the secant is 1 over the cosine of theta. If you multiply numerator and denominator by the cosine, you get sine of theta over 1, or just sine of theta. So we've taken a very complex looking radical and reduced it down to the sine of theta. That is pretty brilliant. And by the way, this type of problem dominates a huge part of calculus 2. And you have to be able to take something, an expression like this, excuse me, that's terrible to work with as far as integration goes, and turn it into something that's simple to work with in terms of integration, the sine function. So that's just a heads up of where you're going to be going in mathematics if you're heading into calculus eventually. All right, that's what I wanted to clean up in this video, just to make sure I hit all the bases so that everybody had a good, proper introduction to proofs and all that fun stuff. All right, now I will see you in the next video series, which is going to be graphing trigonometric functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.